Hi everyone, I hope you're doing well. I'm going to go ahead and get started here with reviewing all of the lab manuals. I think those are the best resources for you to review prior to the exam. Another big thing that I would advise would be to look into your textbook over these sorts of material so that way that you can review it more in depth with maybe other reactions or other pertinent things that might be related to what we've covered. But I think that if you've done all of your notebooks and you've reviewed what I've given as feedback towards them, if you've missed any of the post lab questions, please make sure to either coordinate with one of your colleagues or to ask me if you need any clarification on some that you may have missed, so that way that you can get the correct answer and then you can review that as well. But I will not be going through each post lab question and giving each answer for them in this series. I will just be going through each one of the lab manuals so that way we can cover the topic in a broad sense. So the first one that we covered was recrystallization and melting points. And in this, we needed to know exactly that a pure compound, it's just 100% that compound. There's no mixture. It would be like if you had a pure glass of water. The difference if you had something that was impure would be a glass of water with maybe salt in it, or if you had some sort of like beverage like soda or juice, those would not be pure, right? A pure sample of water would be only water. That's it, no adulterants. So, in that sense, you need to know that in the same way, compounds, if you are to extract a specific compound using something like recrystallization, you would be left with only that compound. So, going forward, this is highly dependent on the solubility of a given compound, and in that sense, we can utilize things that are more soluble in hot solvents than in cold ones in order to dissolve everything into the hot solvent that we use, and then we slowly cool it down, and then once it's been cooled down, then we end up actually precipitating out the product that we want. So we want our product to be only slightly soluble in cold conditions, or insoluble in cold conditions, and highly soluble in hot conditions. So going forward, this is an example of benzoic acid. So please do remember benzoic acid, it's going to be a benzene ring with a carboxylic acid attached to it. That's one big thing that you need to remember. And so the thing that we're separating here is going to be benzoic acid and copper sulfate. And as you can see in water, copper sulfate is pretty soluble, and benzoic acid is not very soluble at all. In methanol, it's the opposite, and then ethanol as well. It looks like benzoic acid is much more soluble. These numbers, they mean the quantity of grams of solute. So 36 grams of benzoic acid is available to be dissolved in 100 grams of solvent, whereas 0 grams of copper sulfate can be dissolved in ethanol if you have 100 grams of ethanol present. When they say 100 grams of solvent, that can be the same thing as saying 100 milliliters of solvent. They're just giving you a weight by weight ratio there. So if you're given a solubility table, that way you can look at and see what you can dissolve and what will be readily left there. So in another form of extraction, you could either use ethanol or maybe acetone to dissolve the benzoic acid out of a mixture of benzoic acid and copper sulfate. But the main thing that we utilized in this lab was to utilize recrystallization. And so here we can conclude the proper solvent to produce solid benzoic acid at 20 degrees Celsius, while leaving copper sulfate in solution is water. In this case, we are precipitating out the benzoic acid and leaving the copper sulfate dissolved into the water. Yeah, and then of course the other solvents would yield copper sulfate and leave benzoic acid in solution. So it just depends on the way that you tackle this problem. That's the way science works. However, in this case, we'd be using water, so that way we keep copper sulfate in solution and precipitate out benzoic acid. Secondly, melting point. We've seen the videos. If the videos are a good thing to review as well of the performing these reactions in lab and experiments in lab. And you use it onto a melting point machine. It's a very rudimentary concept. The melting point differs depending if you have a mixture of two things, and you have something that has a really high melting point and you have something with a really low melting point, but they're in solution together, then they're going to be somewhere in between the two melting points. So that's the take-home point in melting point, because it's kind of a very straightforward concept in chemistry. You just need to know how to obtain it, use the machine. And then of course, if you look at a mixture, then what you can do in order to understand what that melting point is for a mixture. So also please do review the eutectic point chart here. This is pretty important because here you can see the temperature E is the temperature at the eutectic point E. This point is defined as the equilibrium point at which A and B melt in a constant ratio. So at a given ratio of 60% mole percent A and 40% mole percent B, that would mean that at this given temperature that they give you on this chart, they both would melt at that given temperature. So let's just say the hypothetical temperature here would be 70 degrees Celsius. Then that means they both would be melting at 70 degrees, given that that's at 60-40% composition. And this is just an important chart to review. You need to remember your keywords, eutectic point, and other, melting point, such like that. So that way on the test, if they pull that word out on you, it's not out of nowhere. And, maybe some of the test might ask you questions, with regards to using, like in the quiz where you have to enter, you have this a drop down box and you have to choose the words. So, maybe eutectic point could be somewhere in the exam. And then of course, in this case, so that's the word melt at constant ratio. In the case of figure 1.2, mixture compromises 60% A and 40% B, would be called the eutectic mixture. So at the eutectic point, that's the temperature that they both melt in a constant ratio, and that point is defined with this eutectic mixture, is that quantity that is relevant at the eutectic point. Okay. And so that is the main primary thing that's gone through here. So make sure to review the data analysis for this section, and then we can move over on to the next one. Okay. Let's see. Now, thin layer and column chromatography. When we look at this, make sure to understand the concepts that are behind chromatography itself. And in the first one, they're saying that how it was used to describe the colored bands observed when a solution containing plant pigments is passed. And this is just saying how it first started. But the primary concept of chromatography, you should just know, it's separation. Separation. We have gas chromatography, liquid chromatography. There are so many ways of chromatography in chemistry. All you need to remember is just separation is the big keyword here. So the mobile phase is generally a liquid or gas that flows over the fixed stationary phase, which would be a solid or liquid. And that depends on what type of chromatography we're using. So be careful on the test, with regards to what type of chromatography we're discussing in there, because there's normal phase, there's reverse phase, gas chromatography, liquid chromatography. Going forward, we should review that here the partition coefficient is the distance, and the components separating are called migratory bands. They're the individual migratory bands for each compound that's within a given mixture. And then, remember how to calculate your partition coefficient. Make sure you know how to, if you were given a TLC plate on a piece of paper, how you could calculate the given partition coefficient. And I'm not going to stick too long onto here because it's going to go down into TLC down here. But so you should know TLC is thin layer chromatography. Column chromatography we'll cover later. HPLC, we didn't cover that in this class, but that's high performance liquid. And then gas liquid, GLC, we didn't cover, but we did cover gas chromatography, which we will talk about in the next section. Okay, so TLC, remember this. This is our TLC plate, how to calculate the partition coefficient. It's very simple math. Use a ruler, do some subtraction, do some, division of the total distance traveled by the distance traveled by your given compound on this TLC plate, and then that gives you your RF value. And so to know that TLC is a solid liquid adsorption chromatography method. Utilization of the TLC plate is a silica gel plate. That's one thing you need to remember. Another thing is silica gel polar. So that means that non-polar things will stick less to it. The more polar things will stick more to it. So on this instance, the 2.9, more polar stuck to the TLC plate better. 8.3. This stuck to the TLC plate, not as good. Therefore, it means it's more nonpolar or less polar. Those words are interchangeable. You just need to know the word polar. And then remember, more polar, less polar, and then polar versus nonpolar. And then they're the two sides of the spectrum. Okay? So going forward, let's see. Yeah, so the solid adsorbent, in this case, the TLC plate is the adsorbent. It adsorbs the compound onto the plate and then travels with our mobile phase. So in this case, the TLC plate is the solid stationary phase, and then our solvent is going to be our mobile phase in this instance. And the developing chamber is the container, the beaker that you place your TLC plate in. The suitable eluent or eluting solvent is going to be our mobile phase in the case of hexane, DCM, ethyl acetate. There's an abundance of solvents. Just want to make sure it's not too polar, though. The solvents, they want to be slightly polar, but mostly nonpolar. Okay, remember this image here because this is the setup for your TLC. The filter paper we don't always use, but this is in the developing chamber. This is the entire developing chamber. Beaker, TLC plate, solvent. That's everything that's there. The watch glass, that's just to make sure that the solvent doesn't evaporate while you're running it and that it runs smoothly up the plate. Okay. Going forward, you can also know that alumina is used sometimes. And then let's see what else here is important. And I'm going to just be going through kind of fast because this is just a review. We've studied this hard, and if you need more review deeper into it, I would recommend either using YouTube, utilize your textbook, or go into your lab notebook, read through the procedure, really understand exactly what we're doing with these things. Okay, let's see. Okay, so here is the allotropic series here, and so you should know that the allotropic series are polar stationary phases, and the polar stationary phase in this case is silica gel, and this is the increasing adsorption on polar stationary phases. So the given R group over here with a carboxylic acid would be extremely polar, and then on the opposite end with this RHAL, halogen would be extremely nonpolar, and then of course you have like going in reverse order of nonpolar being all the way on the right and then very polar being all the way on the left. And so that is just the way that we can determine how strong that this compound would stick to your TLC plate, because it's all about the polarity. If it's more polar, it sticks more. If it's less polar or more non-polar, it sticks less, and it'll travel more with your eluting solvent because the eluting solvent is non-polar. And so here, the eluting power is found here in figure 2.5. So the eluting power, their inverse, it depends on if your stationary phase is polar or if your stationary phase is non-polar. And we'll be discussing a non-polar stationary phase when we go to gas chromatography. So this is where everything's starting to wrap together now, because at the start, I bring up these phrases and everyone probably was like a little confused, but since we've gone through the full course, now things are starting to wrap up entirely together. So looking here at the eluting power, you would want to know that the increasing eluting power with polar stationary phase, which would be TLC, this is important. This is the one that we're discussing in this section. So petroleum ether, extremely nonpolar, super, super nonpolar. Hexane, toluene, still extremely nonpolar. So here, DCM, dichloromethane chloroform, those are good solvents to use because they are still slightly nonpolar. That'd be good for your compounds that are wanting to move along, but it is also slightly polar, and it's good because you can't go really honestly past ethyl acetate. Once you hit about acetone and up, it'll actually start dissolving your TLC plate, because remember, your TLC plate is polar. So, and like dissolves like, we know that, key idea. And so if you start to try and, put the solvents in that are acetone or propanol or any of the alcohols or water, it'll start to dissolve your plate and you're not going to get it ran. So we want to utilize anything ethyl acetate or less, because that is polar, and less polar going closer down to petroleum ether, which is the most nonpolar next to hexane. And then of course the opposite way switches around. So in the instance of in reverse phase chromatography, you could use water, methanol, ethanol, and then you, of course, you can't go too low on the reverse phase because you encounter the same situation. Maybe I don't know if it would strip the machine of its coating, but it is commonly used to utilize hexane to remove grease from glassware. So we remember when we set up our glassware in the lab, we want to put grease on the joints so that way they don't chip, or that way they don't, when they heat up, that they don't get stuck together and then crack when you try to remove them. So commonly we use hexane to remove the grease on our glassware. So you just have to be careful utilizing anything too nonpolar in a nonpolar stationary phase, and then vice versa. You don't want to use something too polar in a polar stationary phase. So yeah, this is a good chart just to show you the range of polarity, and this is a great thing to review so that way that you know what's more nonpolar and what's more polar. Definitely remember that in a brief scale. And you can also look up, as I showed in class, the polarity index, and that's a great resource to review. Okay, so this is just going through the ways that you can, develop the plate. You might want to review it lightly. Some of it's relative, some of it's a little bit more far out there that might not be the scope of this class. But then the RF, retention factor, is a key phrase and a key equation you need to remember for the exam. And then, so you will take the distance traveled by the substance divided by the distance traveled by the solvent. So in the case of the one that was at the start of this, lab manual, the 2.9, that means it's very polar. It's sticking very well to our TLC plate, only 0.24 RF. However, the 8.3 centimeter one, more nonpolar. Not as nonpolar as the solvent, but very nonpolar. And in this instance, you have 0.69 RF value given. So the main idea here, you could take home message would be that this 0.24 is a polar compound, and this 0.969 is a nonpolar compound. Relative on the scale. It's all a big scale in chemistry. So finally, here we coming into the column chromatography section. And in here, it's a solid liquid absorption chromatography, kind of like the TLC plate. And then in this instance, if we're using silica gel, then we would be utilizing the same exact method that we'd be utilizing as the TLC plate. But instead of it going up the TLC plate, we're putting it onto the column and it's going down the column. So everything is upside down now, if you think about it like that. So see, here's your silica and it separates going down. The TLC plate runs the solvent up, so that's why everything goes up. In this case, the silica is actually, the solvent's traveling down through it. So the most nonpolar will come through fastest, and then the most polar will stick to the silica and come through slowly. So in this case, the first stuff that comes out will be very nonpolar. The stuff that comes out in the middle, medium of polarity, and then the stuff that comes out very last, if you just put a lot of solvent, will be the most polar stuff that comes out last. And again, here's this thing, here's the instance. If you just took a TLC plate and you turn it upside down, you get that result. So, TLC plates, they crawl up, remember that? And then column chromatography, they actually goes down. So remember that distinction. It's still the same thing going on. It's just if you turn it upside down. Okay, so since we covered that, there's not too much there to, discuss. The main thing here is that it's a normal phase column chromatography, polar stationary phase of aluminum or silica gel, and use a combination with organic solvents that are going to be slightly polar, mostly nonpolar. Under these conditions, the allotropic series is described up above, so check that for the polarity one. However, in reverse phase column chromatography, here, this is actually flipped. So the script is flipped. In this case, the increasing absorption goes the other way, right? So the allotropic series for nonpolar stationary phases is the exact opposite, and that's all you got to remember. The most polar is over here, the carboxylic acid, and so that's why the absorption is very terrible on a nonpolar stationary phase, because it's so polar. So you just need to remember nonpolar, polar. What's your stationary phase? And then you can, take the scale from there. It's the exact same scale. It's either just that the arrow is going that way or it's going the other way. It just depends on what your stationary phase is, and then you'll have a relative reference. So all of this wraps together, and that's the great thing about chemistry. You have to get that idea in your head first, and then that way you'll know exactly how to solve the problem given to you. And then this is just describing how much that you would want to use in order to separate a compound nicely, and then the other methods of dry packing and wet packing, where you pour dry adsorbent slowly into a vertical glass column half filled with solvent. And then the other method is to wet pack, in which you make a slurry of the adsorbent and eluting solvent, and then you add it to the column. I prefer dry pack in lab personally, but some people prefer wet pack, and that's just a personal situation on however somebody wants to pack that. So let me just make sure. Okay, that I'm not missing any keywords here. And then here, just to toss out, make it very easy for you, that the 9-fluoronone is way polar because it has this ketone group here. This oxygen can readily perform hydrogen bonding, more polar. The fluorine is nonpolar. It's all carbon chains. So the fluorine on a column, fluorine would come out first, 9-fluoronone would come out last because of the polarity difference. And then make sure here at the bottom that you've completed, all of your post-lab questions and to review them. And once again, if you have any specific questions, I'll answer them. I'm just not willing to hand out all of the answers just in case for, future classes going forward. And so that way that everyone gets their practice with this. And if you need any assistance with these answers, let me know and I'll work together with you to work through the problem. Okay, so moving on to the next one. Let's see real quick. Okay, now let's get into separation of organic compounds by acid-base extraction techniques. Okay, so we're going to partition compounds between two immiscible phases, just like water and oil. We have an aqueous phase and then we have an organic phase given. So adsorption is what we use in chromatography. Extraction involves selectively removing one or more compounds of a solid, liquid, or gaseous mixture into a separate phase. So in this case, we're utilizing liquid-liquid extraction. Remember our core rules here, that our extracting solvent must not react in a chemically reversible way with the components of the mixture, such as that water is immiscible with oil. The extracting solvent must be immiscible or nearly so with the original solution. The extracting solvent must selectively remove the desired component from the solute being extracted. So the partition coefficient being removed must be high, while the partition coefficients of all the other components should be low. So remember, partition coefficient just means the given solubility, the concentration, in this case, the concentration of what's being removed needs to be high, and the rest of the capacity to be dissolved for the other components should be very low in this given extraction. So the extracting solvent should be readily separable from the solute, of course, giving the water-oil situation. And then, of course, the volatile solvents is very good for simple distillation, such as ether, very low boiling point, and other sort of solutes like ethyl acetate, DCM, chloroform. They're all very volatile solvents that are very good for extraction. So most organic carboxylic acids are insoluble or only slightly soluble in water. And what we can do is we can actually deprotonate this acid using sodium hydroxide by the base producing the sodium carboxylate salt, right? Like what we discussed in class. So benzoic acid is insoluble in water, but very highly soluble in organic solution. However, if we utilize the sodium hydroxide aqueous solution onto a mixture with benzoic acid, it actually deprotonate the benzoic acid. And remember the mechanism here, very simple. Hydroxide group takes the hydrogen in order to create water, and then you're left here with the sodium benzoate as a water-soluble compound. So the sodium ion actually participates in ionic interaction with this carboxylic oxygen here, this benzoate. Okay, and so and then once you've pulled it, you have your basic solution of sodium benzoate on the side from your extraction. Then you can go ahead and put in your hydrochloric acid, acidify it, and then the benzoic acid can precipitate out. Again, it's water, not water soluble, so it precipitate up to the top, just like we did in lab. And so on the flip side, using something like aniline or any sort of amine, they have the opposite conditions, right? So in this case, 3-nitroaniline, make sure to pay attention, aniline, this amine group, not water soluble. It's kind of like an oil. So utilize some acid, hydrochloric acid in this instance, to protonate it and make it water soluble with this chloride ion here. And so, yeah, if you protonate an amine with an acid, then it becomes water soluble. So it's very convenient, just like the way that it is convenient for us to use the sodium hydroxide to make the benzoate group of a carboxylic acid. So they have the opposite effects. And that's the key method in chemistry of separating amines and carboxylic acids in aqueous and organic solutions. And then once again, once you've extracted your amine on the side by using your acid, then what you're going to do is have it there, and then you're going to go ahead and add in some sodium hydroxide solution in order to make it basic. And then once again, the 3-nitroaniline would become water insoluble, fall out. Then you can collect it using organic solvent, and it would dissolve readily into that. So, utilizing these methods that we've learned here today, then you can separate these three compounds. You would have them in a mixture, and you would, first hit it with a base or acid, pull out either your benzoic or your sodium benzoate or your 3-nitroaniline. In this case, it'd be the protonated 3-nitroaniline is what they call it, protonated, I guess, and then the sodium benzoate is what they call it when this is in the basic form. So you would utilize your base first to pull out the acid, then 3-nitroaniline is not affected. Now you only are left with 3-nitroaniline and naphthalene in your organic phase. And then what you can do is apply acid to it. The acid would protonate the 3-nitroaniline, pulling that out, and then in your organic phase, you would only be left with naphthalene, because naphthalene does not be affected by acids or bases, so it would stay in the organic phase at all times. Then you would go forward, just like in the experimental, in order to precipitate out the the benzoic acid, and to separately also precipitate out the aniline. So going here, make sure to review your post-lab questions and to remember the mechanisms that go on in order to create sodium benzoate and the protonated 3-nitroaniline. And that's the key message here that you need to remember. Utilizing the solvents, organic solvent, aqueous solvent, they have two phases, and then how you can extract them utilizing acids and bases onto a benzoic acid or onto an aniline. Very straightforward message here today. And so I think that, we can go forward after y'all have reviewed this notebook, and it's a very straightforward experiment here and a really good method in chemistry. Simple distillation. And so here, the main things that we'll want to remember are Dalton and Raoult's law, because they're going to be related here. And as you can see by my notes here, Dalton's law is the total pressure of a given system is the sum of each individual partial pressure. Raoult's law is the pressure of the solution is equivalent to the X of a solvent times P of a solvent, where that's given that the mole fraction of a solvent multiplied by the vapor pressure of a pure solvent is equivalent to the vapor pressure of the given solution. So the total, it's all about the grand scheme of things, the individual parts together, add together, or multiply together in order to create the full system. So going forward, then we can go down here to talk about equilibrium vapor pressure of a liquid at a given temperature, and this is the magnitude of vapor pressure at a specific temperature. And that should be known that vapor pressure is temperature dependent, and it's related to the idea of the kinetic energy in liquid molecules. And so the key idea that we want to go here and understand is that the given boiling point is relative to the pressure on the system. So for this given liquid, the boiling point at 760 torr would be 60 degrees Celsius. Now, if we reduce it down, let's just say to, near 100, near like 110, I guess, would be here on this chart, and there would be a boiling point of 10 degrees Celsius. So the main idea that you want to take home on this one is going to be that concept relating the pressure and the boiling point. Lower pressure, lower boiling point. Higher pressure, higher boiling point. And of course, we covered Dalton's law of partial pressures. The total pressure is equivalent to the sum of all of the individual pressures together. And so in this instance here, we can talk about the pressure of the total is the pressure of the sample added to the pressure of the given air in the atmosphere. Okay, and then going forward, we know about boiling point, and I just made that relative statement there that the boiling point of water, is only 100 degrees Celsius at atmospheric pressure, 760 torr, would be lower if you lower pressure, higher on higher pressure. Okay, and so going into the key point here of simple distillation that we need to understand, it allows us to separate distillates from less volatile substances that remain in a pot residue at a completion of distillation, whether that be a solid that's left there or a liquid with a higher boiling point. It's really good for things, and we need to remember this is the key one here, with the difference in the boiling point of each pure substance greater than 40 to 50 degrees Celsius. If it's less than that, we need to utilize fractional distillation, and we'll discuss that in our next notebook. Okay, so diethyl ether, 35 degrees Celsius, toluene, 111. Definitely we can get that diethyl ether going because it's so low. You start boiling it just a little bit right there near 35, and then it starts distilling off. Then you're left with toluene in your main reaction vessel. So it's a very simple process. That's why they call it simple distillation. We just need to know here the relative system here is talking about if you were analyzing water versus a concentration of sugar in water. So the second curve here you can see has actually increased, or it has actually decreased the boiling point here because it is all relative to the compounds that are within a given mixture, kind of related back to this eutectic mixtures and such that affect the boiling point. So a curve 2 with concentration of sugar and water, it actually, if you go to 760, you would see that it would probably be actually closer to 110 for your boiling point. Whereas on pure water, you would actually only experience at 100 degrees Celsius to be able to boil over water. So in this case, the presence of a non-volatile impurity reduces the vapor pressure at any given temperature by a constant amount. And so in that relative index, that would tell you that since it's reduced it's actually going to require a larger amount of temperature in order to boil it if you are given at a reference point. So in our reference point, that's going to be related to where we talk about the pressure of the given system. And in a given system, our reference point is 760 for atmospheric pressure. 760 torr is equal to 1 atm, which is our given atmospheric pressure in the Earth. And so at 100 degrees Celsius, the water boils readily. At near 110, maybe 115, the water sugar solution would boil. Well, I guess in this case, it's 105 degrees Celsius. So yeah, if you add in something that makes the pressure reduce, then it actually is going to create an inconsistency in the system and would require you to put in more energy to try and boil off the water and get that pure water out. Because we're not just boiling pure water. The pure water takes less energy to do it. This would require more energy. And so the head temperature, remember where to measure the head temperature. Look at your diagrams of the images of glassware that you've already drawn out. The head temperature right at the top of the distillation will be the same for pure water because the pure water is boiling up to the head, and then that's going to be 100 degrees Celsius in the vapor phase, and then it'll cool down coming off of your condenser line. And as the water distills, the pot temperature will rise, right? The pot temperature is down in the heating mantle. That's not the head temperature. Remember that. There's the pot temperature. The heating mantle is the temperature down there. However, the head temperature is going to be 100 degrees Celsius because that's pure water. The sugar is going to stay on the bottom. The sugar's boiling point is extremely high, like 300. And only the water will distill off. And as we go forward, the concentration of sugar is going to increase relative to the concentration of water because the water is distilling off. Then there's more sugar per water molecule within this given reaction vessel. And so that further lowers the vapor pressure of the water. So you have to continuously add more temperature in order to distill off the water. And once again, the water is still going to come out at 100 degrees Celsius regardless. So we already talked about Raoult's law. You just remember how to utilize the mole fraction and how to utilize these equations in this given system. And this only applies to ideal solutions, which is all what we talk about in chemistry. Unless you go into the more advanced classes, and then they'll talk about the non-ideal situations, but that's outside of the scope of this. Make sure to be able to use these equations in order to calculate your mole fraction and in order to use Raoult's law. And then if they're non-volatile like sugar, then it does not affect it in this case, since all non-volatile compounds will be taken as 0. And then of course Dalton's law, very simple. Total pressure is all of the pressures added together. Okay, so make sure to go ahead and review this diagram. They may, ask you what is all here. Make sure you know all the glassware, so that way that if they pull out a glassware and they say, what is this called? You can say, oh, it's a thermometer. Oh, wait, this is a condenser. This is a receiving flask. These are support stands. This is a support ring. This is electric flask. Make sure electric flask also with any sort of flammable system, no Bunsen burners. Clamp. Make sure you know all of these, all the glassware that you've utilized in every lab. I would recommend to remember it, because there's only a certain amount of glassware utilized throughout all the labs. So it's good practice just to know the names of, if they put a piece of glassware in front of you, you can say, oh yeah, that's a thermometer adapter. That's a condenser. That's an adapter, and et cetera, rubber tubing, etc. Going forward, make sure to, review your post-lab questions. And once again, if you have any questions with it, just let me know, and then we can work together, and I'll help you out with any of the questions that you may have missed on your lab notebook. Okay, so let me share this. All right, fractional distillation. So like we discussed with simple distillation, utilized for things that were boiling points for 40 to 50 degrees Celsius difference. However, this one is going to be for a stuff that is closer in boiling point. So let's see if they say here how much it actually is. Looks like they're not describing it, but I believe that if it is too close in boiling point, like 5 degrees Celsius, then it may not even be able to perform fractional distillation. However, regardless, I'm going to go ahead and skip over the equations because it's just a reiteration of what we discussed from simple distillation. However, we do need to utilize this reviewing the liquid line that gives a boiling point of all the mixtures and compounds in the upper curve for the vapor line. So let's look here. Yeah, so looking here at A, the liquid line, and B, the vapor line is important, because then you would be analyzing the boiling of a given compound mixture, such that you have here a mixture of 40% toluene and 60% benzene on this graph. So over here, they're both in liquid phase. They boil. You're boiling off the benzene, and you're leaving the toluene in this instance. So over here, A meets to point B at the vapor line, and then you come down and you can see exactly where you stand at that point. So then in this case, you're having only 20% toluene, 8% benzene, and then you keep going down the line until you come over to having 100% of, in this case, benzene and a 0% toluene over in your receiving flask. And you continuously do this over and over in order to obtain a pure sample, depending on how the mixture goes together and if they can actually perform that. And we'll look at a different compound down at the next graph, so that you can see that sometimes we actually cannot perform this entirely. So you can see the smaller mole percentage of benzene and greater mole percentage of toluene, because more benzene than toluene was removed by vaporization, because benzene has a lower boiling point than toluene. However, they're mixed together, so it has reduced, it has created a different boiling point, because it is now a mixture and is not just a pure sample of toluene or benzene. So going down here, like I said before, you would repeat it again and again in order to obtain pure benzene. And so let's go down. The minimum boiling point mixture of composition Z in figure 5.2, which we'll look at in a second, may be considered as those third component of binary mixture. And they're going to talk about an azeotrope here, which is going to be here. So this is when they talk about Z. This is an azeotrope, and that's what I was discussing earlier, that azeotropic distillation does not work very well in the sense that you will never receive 0% of a given mole A in this case. So you can perform the fractional distillation as much as you want, but once you hit that point, then you're going to be actually performing the reverse, and it's going to be bringing you back more of your concentrate of your mole percent A, and then you can't keep going down the line in a stepwise fashion, just like you did with benzene and toluene. So the main thing to note is something called an azeotrope, and in this instance, the azeotrope does not allow you to actually perform a full pure distillation. So going forward, the lower part of the distilling column is maintained at a higher temperature than the upper part. The condensate will be partially revaporized as it flows down the column. So you have to make sure that you obtain ideal conditions whenever you're performing these sorts of distillations. I'm going to skip that. And then we're going to go down to the idea of the theoretical plates, that once again, the HETP, which stands for the height equivalent to a theoretical plate, is the vertical length of a column that is necessary to obtain a separation efficiency of one theoretical plate. And so this is how you calculate here with this idea of a 60 centimeter long column with an efficiency of 30 plates has an HETP value of 2 centimeters. Very simple calculation, just simple division. And so making sure that you understand the idea of why we have these theoretical plates for the concept of holdup, in which we want to prevent the holdup, because if we have liquid coming down and it's refluxing the distillation, then it can actually mess up our experiment, and that is, the condensate that remains in the column during and after distillation. So we always want to make sure to perform the experiment slowly. That'll provide us with good distillation temperatures. And after all, the more volatile component is distilled, the less one remains in the column and the still pot. And then you're left over with the in the receiving flask of a slight mixture, but mostly of the pure compound you're trying to get. And so the way to perform creating this fractional distillation column instead of just a condenser is you fill the column with an inert material with a large surface area, such as glass, ceramic, or metal pieces, or you can utilize the Figurex column. If you want to review the video for fractional distillation, we showed that as an image. And this has an advantage of a holdup of less than 1 milliliter compared to 2 to 3 for the Hempel column filled with the racing rings. So the Figurex column works out really well for preventing holdup during a fractional distillation. And then the temperature gradient is the temperature between the top and the bottom of the column. And there's going to be a gradient because it's going to be much hotter at the top, and as it condenses, then the temperature will lower, and then of course the still pot's going to be a specific temperature. However, we want to see that the temperature gradient isn't too great, because then you will end up having holdup. You'll end up having it not boiling off what you wanted, and it is all about maintenance in these situations. So the necessary temperature gradient from still pot to still head will be established automatically by the condensing vapors if the rate of distillation is properly adjusted. So like I said, slowly, slow and low, trying to keep those temperatures at a consistent amount to prevent flooding. So this holdup leads to flooding, and that's what you would not want. And that's whenever you have this plug of water a plug of solvent in this case, that'll be sitting inside of your column, and it will mess up the distillation. If the still pot's heated too strongly, and if the vapor is moved too slowly, the column will flood, returning to condensate, and then you're not distilling. So you'd have to lower the temperature, cool it down, start back up, and you have to just slowly, slow and low is the deal with the fractional distillation. And then you can come over and understand this concept of reflux ratio as a ratio between the condensate for every drop of distillate that is obtained. So 10 drops of distillate come down, you get 1 drop of 10 drops of condensate come back down the column. However, 1 drop of distillate comes over down the condenser and into the receiving flask. And so the correct column length is difficult to determine. So, it's all trial and error. It depends on the quantity of stuff that you have in your still pot, how much you're just going to be boiling over. And then here's the one we want. The difference in boiling points between 2 pure components should be no less than 20 to 30 degrees Celsius. So that's going to be our key notes here, right? No less than 20 to 30. And then on simple, it needs to be greater than 40 to 50 degrees Celsius. So anything lower than 40, go ahead and go with your fractional. But if it's less than 20, then you can't even perform it. It's not going to be performed unless you have a very specific setup and everything. But that's way too in-depth for the idea of this So just remember that those numbers, 20 to 30, no less for fractional. And then anything that's greater than 40 to 50 degrees, go ahead and do simple, because that'll be easier. So moving forward, performing this. This is our setup with the fractionating column with the Rieching rings, or the Vischring column. Let me see which one that is again. The Vigurex column, or this one with the fractionating column with the Rieching rings, or any sort of or covering in a foil. There's a bunch of different methods, but remember this setup. Remember the simple distillation setup, and remember the primary differences between the two, because we will not be using the fractionating column in simple distillation. Additionally, make sure to review your post-lab questions here and let me know if you need any assistance with that, as well, to make sure that you understand the concept of performing fractional distillation in order to collect a specific pure sample. So let me switch that one over. All right, now let's go into gas chromatography. So we understand the main concept of chromatography as separation from our previous discussions there. So here, compounds present in volatile, liquid, or gaseous solid are isolated after traveling through a coded column based on substance's size and intermolecular interactions. So remember, for this one, there are multiple parts to this specific type of chromatography. It's not just polarity, right? We have substance's size, intermolecular reactions, and then, of course, the coded column. And so in the Vernier Mini GC, we have a metal column, the nonpolar coating. This is our stationary phase, all right? Then in the mobile phase, we actually are utilizing atmospheric air in this case. The nonpolar coating strongly retains the solutes of the same polarity. So polarity is a big indicator within this type of chromatography. And so, as they say, it mostly retains the solutes of the same polarity. And the organic compounds flowing in the chromatography column are then detected by the sensor, producing the electrical responses from the stuff that you've reviewed, from the data points that we've given, and the videos that we've watched, where you can see the little charts of the electron volts that come out. And that is proportional to the concentration of the compounds. And that's how you go forward to calculate the percentage of mixture from a given quantity that you use in there. And the unique time it takes for a compound to exit after it is injected is called the retention time. So just remember, it's the amount of time that it sticks onto the column as it's traveling through with that atmospheric air. So here's an example of the sample gas chromatogram that we've reviewed. Please review the ones that we've utilized for the data sets within the experiment itself. More volatile compounds will move through the column faster because they're flowing with a mobile phase and not strongly bonded. So even if it may be a slightly nonpolar, if it's highly volatile, it's going to travel faster. So this is the part. It's a multifaceted situation with gas chromatography. It's not so simple like that we did with column chromatography. The surface functional groups on the compound are also a given factor, like we spoke of before. Another factor within it is the molecular weight of a compound to a slight extent, and it's not direct relationship that the heavier the molecule, it'll be slower, but there is an interpreting factor, because if you have things of separate polarity in this instance, but you have a larger compound that is as polar as maybe, say, a smaller compound, the smaller compound is going to want to go through faster. And that's just a direct relation. If we're talking about the polarity, the volatility is, somewhat similar. If we come down to the last factor, we could talk about molecular weight because of the size. So think about it just as the size proportionally, that a smaller compound would travel faster than a larger. But it is still highly dependent on not only the polarity, but also the volatility of that given compound. So when separating compounds with a wide range of boiling points of polarity, it's helpful to raise the column temperature during separation. So remember the factors that we can manipulate in order to do the separation. If the separating is too close together, then what we can do is either affect two things. One, the temperature that is inside of the gas chromatography machine, or the pressure. So temperature and pressure are the two factors that we can actually manipulate in order to obtain better separation onto our graphs. So Once again, of course, we're going to go down here and the data analysis. Remember how to calculate the area of the given peaks, and then how to take those and go forward and perform the percentage of mixture. So review down here. Y'all did a really good job on the post-lab questions, if I'm not mistaken, but always feel free, once again, to email out to me if you need any assistance with any of them that you may have gotten incorrect on turning in your lab notebook. And this part was a very swift procedure. Just remember the key points that we talked about at the start, and then let me go ahead and switch over to our next section. Okay. Now, this one is going to be a very swift one as well, but it is very simple concepts that you need to make sure that you have ingrained for this test, and that way that you can come out well with the stuff that's, because it's a very small amount of quantity for the polarimetry, but it's very critical information and very easy for you to grasp. So primarily the ones that we need to remember are the keywords, dextro and levo. A positive enantiomer rotates a plane in a like clockwise and maybe the opposite way because the camera is facing me. But if you think about it on a clock, going clockwise faction is positive, clockwise positive dextro, and then counterclockwise is levo. And the way that I remember levo personally is left. Left is levo, and left is the way the counterclockwise measure of the clock. So the negative, left, levo, positive, right, dextro, also dextro clockwise, levo counterclockwise. And those are the key points. So really remember, dextro is right, positive, and clockwise. Levo is left, counterclockwise, negative. And so in order for us to analyze this material that we are given by utilizing the polarimeter, we'll use Boyd's law. So remember also Boyd's law. You'll need to memorize this equation. Very simple. The unit of degrees is equivalent to the specific rotation, which is the same alpha character, and within brackets, though. That's the specific rotation, and units of degrees as well can be in inverse decimeter, milliliter per gram, and then L is the path length of the cell in units of decimeter, not centimeter. So if they give you decimeter, remember to divide by 10 centimeters per decimeter. So 1 decimeter is equivalent to 10 centimeter. Then finally, the C, the sample concentration in units of grams per milliliter. So grams per milliliter, just remember whatever they give you, that's the gram per milliliter as your concentration. The main thing that you just want to make sure don't slip up on, and I'll remind you again, just because it's very critical, is that it's in units of decimeter, not centimeter, 10 centimeters per decimeter. And then, of course, specific rotation in units of degrees or in per decimeter, milliliter per gram. And then finally, the concentration. And this will give you the observed optical rotation in units of degrees. So, like I said, it's a very swift experiment, so please make sure to review through the experiment of like how to perform it. It won't be so critical as to where they're going to make you perform this, but you need to understand the idea of dextro versus levo, and then how to calculate it. So memorize Boyd's law, and then remember when you're given the sample height, you see here centimeter, make sure to convert it to decimeter. So divide by 10. Okay, and then I think on this one, let me see. I think all we did was analyze the data on this one. So just remember that when we're analyzing, all of these sugars, that we need to make sure that we also additionally accurately prepare 10 milliliters of 10% aqueous solution. How would you prepare 10 milliliters of 10% aqueous solution? This is a big one. How do you prepare 10% solution? Super simple. This is a critical point, so please remember this. This is going to help you going forward immensely. So 10% solution. Let's just say you have 10 milliliters. So if you wanted 100% solution, that would mean you need 10 grams of your sugar for 10 milliliters of water. That'd be 100% solution. So if we only need 10% instead of 100%, that means you only need to use 1 gram. So 1 gram per 10 milliliter. So it is a relative percentage by weight of the total solution. So if you had 100 milliliters and you want 10%, that means you need 10 grams of your sugar. 10 grams of sugar to 100 milliliters of water is 10%. And then same thing, 100 grams of sugar to 1,000 milliliters or a liter would be a 10% solution. But in this instance, you would use 1 gram of sugar into 10 milliliters of water to make 10%. So 10% of the total solution is your sugar. So remember how to calculate creating solutions and percentages of solution. It's all by weight, very simple. And additionally, please review theoretical yield. I knew that some people were kind of struggling with that. So please make sure you understand how to perform theoretical yield. I'm not going to go through performing it since we've already discussed it so many times in class. But if you do need a refresher on how to perform theoretical yield, there's a lot of resources on Google that I would greatly advise. And yeah, so remember Boyd's law specifically and how to create an aqueous solution. 1 gram per 10 milliliter would be equal to 10%, 5 gram per 10 milliliter, 50% solution. And so then, yeah, finally, dextro, clockwise, positive, right, levo, counterclockwise, negative, left, and Boyd's law. The optical rotation is equivalent to the specific rotation multiplied by the path length in decimeter times the concentration in grams per milliliter. So in the case if you have your 10% solution, the concentration would be 0.1 and it's grams per milliliter, right? So then that would mean that it'd be 1 gram per 10 milliliter. So see how that can kind of work out. 1 divided by 10, then you'd end up with 0.1 as a 10% solution. And I think that's a good enough amount of review for this case. I know it's a very short section, but I wanted to reiterate it over and over so that way everyone understands. So let me stop the share here and switch back over. All right. Now, let's get to the main things of chemistry where they come down to the core reactions. And I'm sure that you've covered this in class before, so we're not going to get too crazy with it, but we'll at least analyze the difference between the SN1 and SN2 reaction. Primarily, SN1, they're both substitution reactions, so that's the S. The N means nucleophilic, and then finally, the only core differences between the two is unimolecular and bimolecular. The reason that we say that is that because in the bimolecular, the SN2 reaction happens in a twofold fashion where the attacking group comes in and the leaving group leaves. So that's why it's bimolecular. Whereas the unimolecular is just the leaving group, and that is the main primarily slow step. Then the fast step has no sort of kick onto the reaction rate of this given reaction. That's why there's the primary difference between SN1 and SN2. Tertiary alcohols follow the SN1 route, whereas primary alcohols follow the SN2 route, and then the secondary alcohols are floating in the middle. Remember, steric hindrance is a big indicator of this. And under acidic conditions, the SN1 reaction can occur, followed by the loss of a water in the rate determining step. I'm sure everyone remembers here from writing out these mechanisms so many times. And the reason that we like these tertiary alcohols is because it forms a stable carbocation by a tertiary carbocation. And so the hydrogen comes in, protonates your alcohol, allowing it to become water, which is a great leaving group. Alcohol is a terrible leaving group, but water is a great leaving group, so it leaves out of the system. You're left here with a tertiary carbocation, and then the chloride group comes in and attacks, finally to create your T-butyl chloride. And then one verification method would be gas chromatography, and the other one, make sure to remember this, is the silver nitrate test. So silver nitrate and ethanol can be utilized in order to see if it will precipitate, and if it does precipitate, then that means we have our good product. So what happens is that we're going to go ahead and add in our silver nitrate into a test tube with a little bit of our T-butyl chloride. Then the nitrate group will actually come in and attack the T-butyl chloride. The chloride group leaves, the chloride group attaches to the silver in order to create the silver halide. In this case, it would be silver chloride because of the chloride group that's on our T-butyl chloride, and then you're left with T-butyl nitrate in the solution. But the main thing is that you would see the presence of the insoluble silver halide that would precipitate out. So remember the key words there of the stuff that we use in order to confirm T-butyl halides or any sort of SN1 halides is by utilization of the silver nitrate, because the nitrate group can come in, displace the halide, and then the silver halide, silver chloride in this instance, is created. Okay, so finally, since we've already gone through SN1, we remember the slow step is the highest part of the reaction rate, and the hump in the rate determining step is the leaving of our water, the protonation and leaving of our water group, followed by the fast step of the chloride, which is not relevant because it's very fast. But the reaction rate in this instance is bimolecular and highly dependent on simultaneously the attack of the bromide and the leaving of the hydroxide. Albeit that the hydroxide group is not a good leaving group, it is okay in this instance because the bromide is a very strong nucleophile and the hydroxide can readily leave by this swift backside attack by the bromide ion. So it converts our 1-butanol into 1-bromobutane. And then finally, we can take it forward to confirm our product not only by gas chromatography, but this time by utilizing sodium iodide. So remember, silver nitrate is for our SN1, and then sodium iodide is for our SN2. In the same sense, so what happens here, if you look actually at our periodic table, you can see that the bromide ion is higher on there, and the iodide ion is lower on the periodic table. And the lower that we go in our halide series, the more nucleophilic. So the iodide is more nucleophilic than the bromide. So what happens is the iodide comes in and performs the SN2 this time, backside attacking, the bromide ion leaves, and what we end up actually making is this alkyl halide, which is going to be the iodobutane in this case, and then a side of sodium bromide. And that, again, you would have an appearance of a precipitate that would indicate a positive result because the sodium bromide's formed, and then you have iodobutane being produced on the side. And so please review through the synthesis so that way that you can see how it goes. But mainly I would say to focus on the mechanism of the SN1 reaction, and then to go forward and review the mechanism as well of the SN2 reaction in case they maybe make you draw out a reaction. Additionally, remember theoretical yield, how to calculate it, why is it necessary for acidic conditions. Great questions here. Make sure to review your data analysis questions, the post-lab questions, and to understand that the SN1 requires your silver nitrate to test, whereas the sodium iodide would be used for your SN2 test because the iodide is more nucleophilic than the bromide, allowing it to backside attack and allow the bromide to leave as sodium bromide. So those are the core principles here of this given experiment, and I'm going to now take us over into the next one. All right, now let's go forward to talk about dehydration reactions. And in this case, like, what are we talking about? Are we talking about E1, E2? Let's figure it out. So acidic conditions in this case to create a alkene in the presence of a Bronsted acid, such as sulfuric phosphoric acid, and it is unimolecular. What is unimolecular? Is that SN2 or is that SN1? So remember, uni, singular, SN1. Bimolecular is SN2. Another way that we would know that it's unimolecular is because we're going forward, we are protonating our alcohol. This is always something that happens within SN1 reactions, is some sort of protonation and action that allows us to take a poor leaving group, turn it into a decent leaving group, such as water, and that's what we're doing here. Then the water leaves, and that's our first unimolecular, only important step, the slow step. Remember your reaction diagrams. The slow step is the key moment there, and then the fast step, which is the dehydration of the alpha proton next to the carbocation, donates its electrons over and gives us our double bond on our alkene. So is it E1 or E2? Well, I'll go ahead and tell you here. This one's an E1. Why is it E1? It's an elimination reaction, dehydration, elimination, creation of an alkene, and it is 1 because of the unimolecular process. If it was bimolecular, which would mean that a group would come in, take away like a hydroxide or something, and immediately the alkene's formed. No, this time we have to have the water leave first, then the alpha proton next to it goes, here's the electrons, and creates your alkene double bond. Okay, so carbocations can also rearrange in performing alkyl or hydride shifts. This may be on the test. I would say too, just understand the key concept here that if you utilize this sort of reaction, the most favorable situation will occur. So firstly, you know that this alcohol group leaves as water, then you have a carbocation. However, this case is only a secondary carbocation, right? Because it's in between two carbon groups. So we can have our alkyl group walk over one, then we're left with a tertiary carbocation, which is superiorly stable, creating a very nice double bond here in the center with our major product. Then we can have our minor product, which would have our double bond onto a secondary situation. And then finally, we have our worst minor product of a primary alkene. And this would be very small amount. This is the most favorable. It's most stable, most sterically stable, least steric hindrance, most stability for the pi cloud electrons all around. And the main take home point is that we can perform that hydride or alkyl shift whenever we create that carbocation. So that way that the compound can sort of rearrange itself to go to a more stable form instead of just having that carbocation all the way out on the side and very desperate for electrons in that case. It actually, the compound will rearrange itself and allow the alkyl shift to happen so that it's more stable in the center and ready to prepare that alkene. And it's a more stable alkene as well, being that it is in the center. Okay, and so I'm going to skip over the entirety of the other forms of dehydration. I think those are irrelevant with regards to the stuff that'll be prepared for on the exam. So greatly understand the post-lab questions because y'all did awesome on this from what I've seen so far. I think everyone blew this out the water, and you just need to make sure that you know here the method, the mechanism. There's only a few mechanisms in this course, so remember the mechanism of our E1. Then also remember that you can make major and minor products. So if you didn't get the dehydration reactions correct for the ones that possibly could have had side products, then please either review with me or go forward and review yourself onto what that you can create from these side products that maybe are less stable, such as the ones that we reviewed up here with how this can be created. It can be created. It's just in such a low quantity because it's unfavorable in this instance. So make sure to review those reactions here because there may be a few of them. If you didn't write down any side products, then you may have missed it, and you can feel free to contact me regarding it. It's because there are some of them that do create other side products that are minor products. But, the major products are very key. It's just that maybe you might lose half a point if you don't also put the minor product there as well. So make sure to create your minor products. Okay, now let me go and pull over to our final one here. All right, great. So let's come to our final lab here, and this is the bromination of Stilbene, which is a great thing for us to review because it is all wrapping together all of these ideas of dehydrations and substitution reactions. And we just covered over an alkene, the double bond, right? So here we're going to go ahead and talk about this electrophilic addition mechanism, which is a different form of addition. Instead of it being a substitution, it's going to be an electrophilic addition onto this given double bond. So what happens is that actually the double bond acts as the attacking group. Is the pi electrons of the alkene attack the electrophile. So instead of the nucleophile coming in and being the attacker at the start, this actually uses the pi electrons here and donates it to this electrophile in the given system, because the electrophile it wants to hit that 8 valence electrons. It wants to be happy and satisfied. So the pi electrons go out, they attack the electrophile. Then what we're left with is a carbocation on our alpha carbon. So then the nucleophile in the environment can come in and actually attack, leaving us with one attached electrophile and one attached nucleophile onto that original alkene group that we had there. So this is the core ideas here. Remember your buzzwords. This mechanism is called electrophilic addition mechanism. Another buzzword, electrophile. It seeks electrons. It really wants to receive an electron. And then the other one, nucleophile, it's center seeking, nucleus seeking, and it wants to attack and it wants to donate. The nucleophile wants to donate, the electrophile wants to take. So the most common ones for these halogenations are going to be the chlorination and brominations. And in this case, going forward, we would look here at this production using chlorine. And what would happen is, firstly, this is the first step of the mechanism. The pi bond attacks the electrophile. In this case, one of the chlorines will act as our electrophile. Then the electrons will move over to the other chlorine group into the system, and it actually has the chlorinium intermediate. So remember that since the pi electrons are donated out, it's kind of like it's donating from both carbons, and so it's bonding both to the chlorine or bromine for the future reaction we're going to talk about. And the chlorine is slightly electropositive now because it's being bonded by 2 instead of just 1. So what happens is, since it's slightly electropositive, it wants to let go of that for someone else to come in. So what happens is the chlorine comes in and backside attacks in SN2 fashion, leaving the one chlorine group down and the one chlorine group up. So this is the formation of our dihalide via the chlorinium intermediate. And also, the brominium intermediate is going to be the one with the bromine. So remember the buzzwords here: chlorinium intermediate and brominium intermediate. And so the result of these sort of attacks onto our halogenated products are going to be anti-addition. That's called anti-addition, creating the trans product where you have one chlorine up, one chlorine down, vice versa with the bromine, one bromine up, one bromine down. The same effects occur within the brominium ion intermediate reaction. And so here, this would be the product. So you see that our bromine is out of the plane, and then the other bromine is coming into the plane. So as you can see, like we spoke before, the anti-addition, they're trans. If they were cis, they would both be on the same side, but they're not. They're going to be trans anti-addition. And remember that we also discussed that we would not be using liquid bromine within our lab. We'd be using the organic salt pyridinium tribromide in order to create this. And so if you wanted to look at the creation of here, remember it's only one-to-one stoichiometric, one-to-one stoichiometry in this reaction. So the pyridinium tribromide can actually, in equilibrium, dissociate to create bromine and the equivalent pyridinium bromide on the sidelines. So it actually gives us the two bromines we need. The one for the electrophilic addition, where the bromine acts as the electrophile, gives its electrons to the bromine, and then that bromine that's in solution acts as a nucleophile and attacks anti or trans to the alkene. Well, in the case of the brominium intermediate is what it would be at that point. And so finally, we would have an unknown stilbene, a trans or cis stilbene within this reaction. And I think that y'all did really well on that one. So the main thing, I would remember that the melting point of trans is extremely higher than the melting point of the cis. And so in this case, we additionally are going to perform the silver nitrate test because silver nitrate responds with bromines in a given system. In this case, it's going to be a tertiary bromine. So then what's going to happen is it's going to produce the silver halide and the nitrate groups that come in, and you'll have on the side the silver bromide. So once again, bisanol dihalides react with the alcoholic silver nitrate in order to form the precipitate of silver bromide. In this case, it'd be silver bromide because the nitrate group comes in, it displaces the bromide, creating silver bromide as a side product. So please review here your post-lab questions. And once again, if you have any questions regarding any of the post-lab questions, I can answer them into your personal email. Just let me know if you have any issue with many of the mechanisms that are in any of this stuff. And then otherwise, just review through everything that you've done so far, review your notebooks, remember the steps and all of the equations that we've discussed, remember the mechanisms, those are the core ones, and then just remember how we perform this reaction and why we perform this reaction. So I hope you do well on your test. Feel free to contact me at my email and let me know if you need any help. All right, well, thanks for watching the video, and I hope you have a great